a brief introduction of my research lab and currently ongoing research. So we are basically focused on the application of renewable energy, especially solar, biomass, heat energy in absorption cooling systems, desalination systems, atmospheric water generators, solar thermal collectors with the secondary reflectors, hybrid solar cookers, and energy storage, especially waste change materials, then biomass briquettes and biodiesel extraction, and nano embedded adsorbents and PCMs. And recently, we are focusing on developments of green adsorbents, that is adsorbents from biomaterials in association with the University of Newcastle. And of course, then as we all know, the solar systems are intermittent in nature. It's very unpredictable nature of solar insolation, relative humidity, dry bulb temperature, and so on. So the dynamic optimization is very important for these energy kind of systems. Hence, the ethical or responsible AI in energy systems are being explored, which may lead to the industry 4.0 products. And these are the things I mentioned here. And this is my team. I have a team of postdoctoral scholars working from different disciplines, including mechanical engineering, computer science, electrical engineering, and a team of PhD scholars and MTech and Tech students. So we have collaborations within the institute within India, including IIT Delhi, IIT Roorkee, MNIT, and IIT Calicut, and some industries. We have an industry partner, Unique Dynamic Technologies. Then atmospheric water generated supplies, and we have some works with Kerala Water Authority and others. So we have a few international collaborations too, including Sofia University and the University of Newcastle. So with the background, I would like to begin my talk on why solar cooling systems are relevant nowadays, and what is the state of art of these technologies. So before that, we all know why nowadays researchers and scientists are talking about two important global issues. Number one is the energy crisis, and number two is the environmental issues, particularly the climatic change. We all know the fossil fuels are being powered human development over a century. The combustion of all these kinds of conventional fossil fuels, including coal, oil, or natural gases, are responsible for release of greenhouse gases like carbon dioxide and methane, which ultimately leads to the climatic change. So, the recent research based on satellite data reveals that there is a trend, that means you can say in between 2002 and 2023, that is a span of 21 years, Antarctica loses an average of 150 million metric tons of ice in every year. This massive ice slopes has significantly contributed to the rise in global sea levels, highlighting the urgent needs to address the climatic change. The other concern is the source of conventional fossil fuels. A recent study conducted by MNR indicates that at our current rate of the consumption of global oil and gas reserves, that could be exhausted within the next 50 to 100 years. So more importantly, a study conducted by Harvard University estimated that in 2018 alone, over 8 million people died as a result of the fossil fuel pollution. That means the air pollution from burning of fuel like coal, oil, and conventional fuels accounts for roughly 1 in 5 deaths in worldwide. So these are the facts in front of us, including some studies conducted at our capital city, Delhi. It is having worst air quality index in 2024. So that means these are the some news. Appeared in daily. Famous Indian Express news daily. A study conducted by IIT Delhi in 2021 says this basically it is due to the biomass burning emissions, likely from the local burning of wood, coal, or roadside trash for heating or cooking purposes. These are the facts we have. So that means nowadays actually people are thinking about something we have to learn effectively how they are constructed their shelters, houses, and including how effectively they utilize the renewable energy resources like solar, wind, and hydropower to meet their daily needs. So, in fact, if you are talking about the global energy statistics too, in 2023, there is a significant increase of 627 terawatt hours of energy demands, in which China actually placed the first. They have a rapid growth of 6.9% of energy demands, and India followed as the next major contributor, marking about an increase of 5.4%. So these are the facts what I have mentioned earlier, and this is this yeah. Coming to this picture, see one of the major advantages that nowadays, as you know, all central or state governments are very much interested to improve the contribution from renewable energy sector, including solar, biomass, or wind energy. So at the current state of around the 61% of the energy produced in India is derived from the conventional fossil fuels, and the contributions from the renewable energy sector is almost 39 to 40%. Okay, so with this background, so I would like to start my topic, that is solar cooling systems. So a study conducted by Energy Statistics of India reveals that India ranks first globally in fruits and milk production and second in vegetable production. But the problem is that there is a lack of post-harvesting cooling facilities for these fruits, vegetables, and the milk. Due to the lack of post-harvest cooling facilities, about 25 to 30% of the fruits and vegetables are being lost, and around 3 to 10% of the milk. That means around 18.5 billion US dollar equivalent amount of amount has been wasted in about 54 crops. So there is a serious lack of availability of cold storage facilities in India and Kerala. So we have a lot of conventional cooling facilities are available to store all these perishable food items. So these are the statistics. I want to show this. There are plenty of million tons of food items, oil seeds, sugar cane, fruits and vegetables, milk, fish are being produced in India and also in Kerala too. A lot of tons of spices, rice, coconut, rubber, all these commodities need to be stored in proper way. So what are the cooling options currently we have? We have plenty of cooling options available. The universally accepted cooling technology, that is vapor compression systems, are available. Evaporative cooling systems are available. Absorption chillers are available. Radiant cooling systems are available. But what is the problem with these conventional techniques? As we all know, these vapor compression refrigeration systems are driven by high grade energy or mechanical work for its operation. So being that's the number one issue. Number two, almost all refrigerants compatible with the VCR systems are having high global warming potentials. Then miscellaneous factors like noise, vibration, electrical grid dependency. If you are talking about the evaporative cooling, it is having limitations. It is purely depends upon the climatic conditions of relative humidity and wet bulb depression, and water consumption issues, microbial growth issues, air quality issues, temperature drop concerns. Then if you are talking about the absorption chillers, these absorption chillers are pivoted around the limited options of either lithium bromide water or ammonia water systems. It is most effective for very high capacity applications. Then it's a very low coefficient of performance. It's bulkiness natural. Radiant cooling systems is also having its own limitations. So that means we need a system, we need systems or cooling facilities which can be easily driven by low grade energy resources such as heat, and it should be scalable to low, medium or high capacity applications, and the refrigerants compatible with that systems should be environmental friendly, and that means it should have a zero ozone depletion potential and global warming potential. So if you are talking about the solar cooling systems, the concept of solar cooling systems is not a new one. Actually, the concept of solar cooling systems was introduced long back ago by Otto Moore. He was able to describe the correct components needed for a solar refrigerator. But you know, the people ran away from the technology introduced by Otto Moore because of two reasons. Number one, as we all know, the 1920s and 1930s are regarded as a revolutionary period of the refrigeration and air conditioning industry. Why? Because during that period, a large number of highly efficient compressors and turbines were introduced into the market. And number two, a large number of thousands of refrigerants, you can say, with the trade name of Freon, was introduced by DuPont into the market. So the researchers and people are very much interested to combine these technologies, combine these highly efficient compressors and turbines, and utilize a wide variety of refrigerants introduced by DuPont. So make it as a compact system which can be effective for any type of applications, for storage or comfort applications. So people were not interested in automotive work. But in 1970s, people started to talking about the energy crisis. In 1990s, about the environmental issues. So then the researchers the researchers across the globe just started to rethink about the automotive. That is why if you are going through the literatures of solar cooling systems, you can find a large number of papers published after 2000, 2010. All motivated from Otto Moore's work introduced a very long back ago. So basically, the solar cooling systems, why the solar cooling systems are important? Other fact is that according to the Bureau of Energy Efficiency in India, about 45 to 50% of the energy produced in India is being utilized for the cooling applications. That includes both refrigeration and air conditioning. There is also another study conducted by International Institute of Refrigeration. About 17% of the energy produced is being utilized for a refrigeration application. The other fact is that if you consider the variation between the energy and time, we know that during the morning time we need more heating, more during morning and night time rather than cooling. But during the daytime, whenever the availability of solar radiation is maximum, the demand for cooling is also maximum. That means the availability of solar radiation and the demand for cooling both are in phase. That means there is a huge potential for the exploration or the utilization of solar radiation or solar insulation to operate these refrigeration systems or cold storage devices. That is why the solar cooling systems is having that much relevance nowadays. Basically, these solar cooling systems are classified into two types. One is thermal driven systems and another one is the electricity driven systems. Either it can convert the solar energy directly into electricity by means of photovoltaic systems, and that PV panels integrated to the VCR systems or thermoelectric cooling systems to produce refrigerating effect. In other way, converts the solar energy into thermal energy or heat by means of suitable collection systems, solar thermal collectors, including flat plates, parabolic evacuated tube collectors, and convert that heat energy or solar thermal energy to turbine cycle, vapor compression cycle systems, etc. Again, the sorption-based cooling systems are classified into two. One is open sorption and another one is the closed sorption systems. Open sorption systems includes the solid desiccant systems and the liquid desiccant systems. Closed sorption systems are again classified into two, either adsorption or absorption. So these absorption systems are having different types, including half effect, single effect, etc. The adsorption systems are classified into physical and chemical adsorption systems. That depends on the forces. So the solar electric cooling system is very simple, as I mentioned earlier. There will be n number of solar panels connected by units of charge controllers integrated to the electric motor that drives the compressor of the VCR unit. But it is not cost effective one, it is bulky in nature too, and its initial and operating costs are very high. So other option is the thermal cooling system. That is what I will be focusing on today's presentation. That is solar adsorption cooling systems. The concept of adsorption is not a new. The concept of adsorption was introduced long back ago in 1881 by a German physicist called Heinrich Kaiser. But the application of adsorption in different mechanical systems, including cooling, desalination, or water generator kind of systems, is still a new nascent technology. There's a lot of potential to improve. So why these adsorption systems are relevant? As I already mentioned, if you are talking about solar absorption systems, it is bulky in nature. It is most effective for very high capacity applications. If you are talking about the thermoelectric cooling systems, it is effective for very low capacity applications. But we need a system that can be effectively utilized for low, medium, and high capacity applications. The refrigerants compatible with that system should be environmental friendly nature. That means it should have zero ODP and GWP, and the systems should be able to driven by low grade energy resources like heat. That is why the solar adsorption cooling systems is having that much relevance. So it is slightly different from the familiar system that is absorption. Absorption, as we know, if it is ammonia water system, this is a bulky phenomena. The molecules will be penetrated together and converted into a liquid solution. But adsorption is a surface phenomena. There will be an adsorbent and a refrigerant, and the refrigerant particle will be entrapped on the surface of the microporous or mesoporous structure of the adsorbent. It is a surface phenomena and depends upon the bonding. If it is a weak van der Waals forces, that leads to the physical adsorption, and if it is strong chemical bonding exists like the alkaline earth products, that leads to the chemical adsorption process. So basically, the adsorption cooling systems have four different processes. Number one is the isosteric heating process. Number two is the desorption process, that is an endothermic process, it needs heating. Then isosteric cooling process, then adsorption process. Adsorption is an exothermic process. So this is the most simple kind of single bed adsorption system. For the simplicity of my explanation, I would like to divide this one into two circuits. Number one is called a refrigerator circuit, and another one is a solar collector receiver circuit. If you look at the components of the system, the components such as the condenser, expansion device, and the evaporator are similar to that of the universally accepted vapor compression refrigerator system. The only difference is being in the extent of compression process. In vapor compression process system, it is the mechanical compressor, that is a work operated device, is responsible for taking the refrigerant vapor from evaporator pressure level to the condenser. In this case, the mechanical compressor is being replaced with a thermal compressor, or it is called adsorbent bed, that is responsible for the is a heat operated device, it needs heat energy as the input. So that is the requirement of the solar collector receiver switch. The water will be heated by utilizing the solar insolation available, and the hot water will be acted as a heat source in the thermal compressor. So initially the adsorbent bed will be filled with a sufficient quantity of adsorbents. There are plenty of adsorbents available. If it is physical adsorbents, maybe activated carbon steel and silica gel kind of things will be filled here. And the refrigerants compatible with the adsorbents, maybe methanol, ethanol or ammonia, it will be absorbed in the bed matrix. For the desorption, it needs heating at a constant concentration. So if it is methanol, it reaches around 64 degrees Celsius for the desorption. If it is ethanol, around 17 degrees Celsius, that depends upon the refrigerant adsorbent combination it will vary. So once it attains a sufficient desorption temperature, it will be desorbed from the bed matrix, then condenses, expanded and evaporated by taking the latent heat from the space to be cooled. And then this will be circulated with the cold water, that is water at the room temperature, making it favorable for the adsorption process. So being it is a single bed system, it is intermittent in nature. So this is the components of the system that we have developed, and the performance of the system basically depends upon the performance of this adsorbent bed. This is the novel adsorbent bed integrated with the different types of fins and others. This is one we have patented recently, and the problem with the intermittent and the single bed system is intermittency in nature. So make it somewhat continuous. This system is modified by integrating with another bed. This is a two bed system. It consists of a common condenser, expansion device and an evaporator. There will be two adsorbent beds and a common input energy source. And if the bed 1 is subjected to isospheric heating and desorption, the valve V1 and V2 will be open, V3, V4 will be closed. So the hot water will be circulated around the bed number 1 and the cold water will be circulated around the bed number 2, so that it will be ready for absorption and cooling process. So the refrigerants desorbed from the bed 1 will be condensed, expanded and evaporated, and then it will be absorbed in the bed matrix of bed 2. Once the desorption the bed 1 and absorption the bed 2 completed, this direction will be reversed. Again, it will be condensed, expanded, evaporated, and then absorbed in the matrix 1. This is a two-bed system that we have designed and developed, available at the Energy Research Lab. So one ton of system. Another system is the heat system integrated with the heat recovery. Why? Because the adsorption process is an exothermic process. A huge quantity of heat is being released during the adsorption process. So for example, if it is activated carbon methanol, around 1100 kilojoule per kilogram of energy is being released during the adsorption process. It's a huge quantity of heat. If if you are able to extract the amount of heat released during the absorption process, the amount of energy input to the thermal compressor can be reduced. That will increases the overall coefficient of performance. That will increases the overall specific cooling power. That will reduces the cycle time of the system. This is sort of system, a heat recovery system that we have developed. And the difference is that there will be two working fluids circulated. One will be acting as the heat source and another will be acting as the cooling source. This cooling source may be terminal oil kind of things will be used to recover the heat. This is another system that is developed in the lab. The system so far I have discussed utilizes sensible heat for the desorption process. So this is the third version of the system. It utilizes the latent heat of condensation in the heat pipe to desorb the refrigerant. That means a heat pipe will be integrated with the system. Heat pipe, as you all know, it has an evaporator and a condenser section. The evaporator section will be integrated solar collector as shown here. This receiver engine will be acted as the evaporator of the heat pipe, and the condenser section will be integrated inside the absorbent bed. So what happens is, when the solar installation falls on the solar trough collector, this water will be evaporated and the steam will be driven to the condenser part of the condenser part of the heat pipe. So that will be surrounded by the adsorbents charged in the bed matrix. So during the condensation in the heat pipe, due to the latent heat of condensation, this refrigerant will be dissolved, then condensers expanded and evaporated. So the amount of heat utilized or supplied in the bed will be of higher magnitude due to the latent heat, so that the cycle time will be reduced. So this is another system, that is a cascade system similar to the cascade vapor compression system. Similar to that of AVCR system, it is having a common evaporator and a condenser assembly. There will be a top cycle. Top cycle will be driven by R134A, and the bottoming cycle it utilizes R507A as the refrigerant. So the evaporator side of the R134A top side will be acting as the condenser of the bottom side. So this is the cascade system, and this is another system. It's a propelled system. In order to avoid the intermittency, this all operated with PID controllers. All valves operated with the PID controllers. If the bed 1 is subjected to isosteric heating, bed 2 will be subjected to desorption process, bed 3 will be subjected to isosteric cooling, and bed 4 adsorption. The beds in a sequence of different processes involved in the adsorption cycle, so that the system will be continuous. So another system we have made is the heat recovery system, that is integrated with an IC engine, a 4-stroke diesel engine available at the heat engines laboratory. So the engine exhaust gas will be taken out, and that the valves V5 and V6, if the bed is subjected to heating and desorption, valve V5 will be closed and V6 will be opened. The engine exhaust gas will be allowed to pass over the bed. We know that the engine exhaust gas still it is having very high enthalpy content, high heat content. The bed needs only around 50 to 60% for the desorption process. So the problem with all the systems I have explained now is having the limitation of very low vibration performance. The main obstacles for the commercialization of such technology is its COP is in the range of 0.2 to 0.6 only, and the SCP value is also lower side. So these are the hindrances to the commercialization of such technology. So there are 3 options for the improvement of performance of such systems. Either we have to integrate the conventional, this adsorption system with another conventional type of cooling systems, or thermodynamic modification of the system, or this is the most important research area, that is the performance of the entire adsorption cooling system. Basically, it depends upon the performance of the adsorbent bed. The adsorbents integrated with the adsorbent bed, normally if it is activated carbon, it is having very low thermal conductivity of the order of 0.14 watt per meter Kelvin at room temperature. That is very low. Being it is transient systems, it needs very high thermal diffusivity for the whole adsorbents and refrigerants. At the current status or commercially available adsorbents are having very low thermal conductivity and thermal diffusivity. So the use of adsorbents with better adsorption and desorption characteristics is very much important for the improvement of the systems. These are the 3 areas where this research is basically focusing on to improve the performance of the ADS systems. I also have done plenty of tricks in these particular aspects. Number 1 is the adsorbent part. Basically, the adsorbents are classified into 3. Number 1 is physical adsorbents, chemical adsorbents, and another interesting area is the composite or consolidated adsorbents. The physical adsorbents are either activated carbon, zeolite, silica gel. These are having limitations of a low value of thermal conductivity, thermal diffusivity, and thermophysical properties. Chemical adsorbents like alkaline metal chlorides like strontium chloride, barium chloride, etc. These also having problem of stability and desorption temperature. So we need ideal adsorbents. That means the adsorbents, physical and chemical adsorbents can be impregnated or consolidated together to make it as a composite adsorbents. That is a new research area in this field. So consolidation or composition of adsorbents make it as a new combination which is having very high thermophysical properties or desirable thermophysical properties. This is one of the composite adsorbents we have developed, impregnating silica gel with a metal organic framework and adding PVP as the binder to make it as a new composite adsorbent. It should have the desirable properties of porosity, area, thermal conductivity. If you are increasing the pH area, there may be chance of reduction in the thermal conductivity, and again there should be a trade-off between these two. So sometimes we have to go for more functionalization or some other chemical treatments to increase the thermophysical properties. So this is one of the composite adsorbents we have developed. Activated carbon impregnated with the expanded graphite, silica gel, and the MOF, finally converted into a composite adsorbent. And the same composite adsorbents we tried with the commercially available activated carbon, which is having thermal conductivity approximately 0.14. The composite adsorbents, that is activated carbon impregnated with the silica gel and the MOF, is having thermal conductivity of the order of 0.37 approximately. And the same composite adsorbents charged with the available solar adsorption cooling facility. The experiments are conducted. The activated carbon, that is commercially available activated carbon with ethanol, is having COP of 0.68, and when it is tested with composite adsorbents, its efficiency of COP improved by around 17%. Similarly with the methanol as the refrigerant. So that means composite adsorbents needs to be explored in detail to avoid the obstacles or the limitations of the conventional cooling adsorption cooling systems. That means if you are using the conventional adsorbent bed, we can expect COP around this 0.4, 0.6 range or 0.2, and cycle time will be 30 to 45 minutes. With these composite adsorbents, there will be significant reduction in the cycle time and enhancement in the heat transfer coefficient. This is another composite adsorbent I have mentioned. This is another potential area of research, that is the green adsorbents. That means conversion of waste materials or biomaterials into the useful composite products. So we have tried with different biomass materials, including rice husk, straw, waste, nutshells, orange peel, banana peel, converted into this activated carbon that can be utilized in adsorption cooling. And also another potential area of research, that is carbon dioxide capture and the hydrogen generation or water splitting applications. Then coconut shells, bamboo, sewage sludge, cotton, etc. All these biomaterials can be effectively converted into these suitable adsorbents. After further modifications that can be employed in water treatments, removal of heavy metals, microplastics, or even desalination systems, drug delivery systems, carbon dioxide capture, etc. So this is the one of the green adsorbents that we have developed from the orange peel. Orange peel finally converted into useful activated carbon after a series of chemical activation and dry processes within the facilities available at TKM College of Engineering. Finally, this orange peel converted into this activated carbon. So again, same activated carbon for a different activation temperature is being compared with the commercially available activated carbon having thermal conductivity of the order of 0.13 or 0.14. There is a significant improvement in the thermal conductivity, and also the same thing is tested with the available experimental test rig, and we can see the significant improvement in the COP due to the improvement in the PET surface area and thermal conductivity. These are the another methods for producing green adsorbents for different applications, including bentonite type clay minerals and geomaterials can be converted into useful products. And this is the concept I have mentioned earlier, from waste to resilience, converting the waste materials, available materials into useful adsorbents that can be effectively employed for different applications. So even clay minerals and geomaterials can also be converted into these systems. So another way to improve the COP of the system is the integration or a hybridization of adsorption systems with the already existing or universally accepted cooling systems like vapor compression, steam ejector, thermoelectric cooling, or combination of ejector and thermoelectric cooling systems. This is the one of the system proposed by Professor Dutta et al. From IISc Bangalore. So what he did is, actually he experimented with a normal vapor compression unit that is having mechanical compressor, condenser, expansion device and evaporator, and conducted a number of experiments and estimated the work input to the system. And then the system is integrated or converted into a hybrid system by integrating a thermal compressor before the mechanical compressor units. So the whole compression process will be taking place partly in the thermal compressor, then after intercooling, then supplied to the mechanical compressor. So partly it will be compressed with the thermal compressor and then the mechanical compressor, then estimated all the work required or heat required to the system. If the thermal compressor is integrated before the mechanical compressor, there should be an intercooler. Well, as you all know, before supplying to the mechanical compressor, this refrigerant has to be cooled to the normal temperature conditions. So then he tried with the different configuration, first the mechanical compressor and then the thermal compressor. The advantage is that you can eliminate the intercooler in between these two. So in that case, estimated that around 38 to 40% of the energy saving is obtained for this configuration, where the compression is carried out in multiple stages, partly in mechanical compressor and then in thermal compressor. This is another system integrated with an ejector system, so similar to that of our normal steam ejector system. So this is the novel research happening. It's a very important, very interesting research. Having thermoelectric modules, so tech modules, are integrated with or sandwiched between two adsorbent beds. This adsorbent bed, when it is subjected to the adsorption process, release huge quantity of heat that will be taken and then transferred to the desorber bed. Absorber reduced. The system where it is being going on, in that case, the COP, this is the maximum COP reported in adsorption cooling systems. This is another sort of systems integrated with the thermoelectric and the ejector systems for improving the efficiency and reducing the cycle time. So in a nutshell, so this type of adsorption cooling systems are being implemented in certain buildings, certain research or commercial buildings and some office buildings. But if you are looking at the adsorbent refrigerant combinations, all relies on physical adsorbents like the silica gel, activated carbon and zeolite. These all having problem of degradation and requirement of high energy input and very low this thermal diffusivity and thermal conductivity. That means the cycle time will be on the higher side. This is a practical system installed at Chile and Australia, Germany, even India. There is an institute called TERI at Delhi. So they have installed a unit run by silica gel and water supplied by newly dynamic technologies and dry air. So this is actually that they have employed for the office cooling. They replaced this vapor compression air conditioning system with this silica gel water absorption chiller. So similarly, Shanghai Research Institute, they have developed around a 20 kilowatt capacity system run by concentrating panel collectors, and the European sun absorber system. There are plenty of research being reported from different parts of the globe, but almost all systems relies on silica gel or zeolite or even activated carbon only. That means physical adsorbents. So now I will be touching a little bit on water desalination purification systems also, apart from these cooling systems. So why these desalination, adsorption desalination systems are important? As we all know, according to World Health Organization standards, about 97% of water available on the earth is saline in nature, and only 3% of water is fresh. Out of the 3% of fresh water, more than 2.5% of water is locked in glaciers. Therefore, that means humanity rely only on 0.5% to meet their own needs. This is a UN World Water report. So that means we need new systems or some systems that can effectively convert this saline water into potable water, or by some other means to generate potable water. So this water scarcity can be addressed through three techniques: either transfer water from one location to another location, that itself has its own limitations; otherwise convert the saline water into the potable water; or extraction of water from the atmospheric air. We know the atmospheric water generator systems. But there are a lot of desalination, commercially desalination systems are available. But all conventional desalination systems have its own limitations. This is the recent article came in New Indian Express. Sometimes we may thought that Kerala is blessed with plenty of water resources, plenty of river, sea, water resources, plenty of abundant rainfall. So we may feel, sometimes we may feel that the water scarcity may not be an issue for us, but this is the one of the news appeared recently is Bangalore days in Kochi. We all heard about a severe drought happened in Bangalore recently. So similar, immediately after that, a severe drought reported in Chellanam area, that is near Kochi. A severe water drought happened. This is actually, you can see a girl crossing a road after after taking water from roadside with the public tap. This is in the Nedinganda part of Trivandrum. So that means there are a lot of areas where water scarcity is severe. Even though we have plenty of water resources available in India as per the report from Central Water Commission, and we have a lot of water resources in Kerala as per a report from Kerala State Planning Board and the Kerala Water Authority, but the problem is the availability of potable water. As I mentioned earlier, availability of potable water is very less. So we have a lot of desalination techniques, including thermal desalination and membrane desalination. That means MS of a multi-stage flash distillation systems, multi-effective distillation systems, vapor compression distillation systems, and the most widely employed one, reverse osmosis technologies. All these conventional desalination techniques has its own advantages and limitations. The main limitation is its high energy consumption and operational cost, the requirement of the high infrastructure. So again, we need a system that can be effectively run by low-grade energy resources rather than work-operated devices. So that is why, again, this adsorption-based desalination systems are having that much relevance nowadays. So this is a simple adsorption desalination system. It also consists of an evaporator, an adsorbent bed or a thermal compressor, and a condenser. This is an open cycle system. So this saline water charged in the evaporator will be subjected to flash evaporation and then adsorbed in the adsorbent bed matrix of this thermal compressor. Then it will be desorbed by means of a heat source, and then it will be condensers, and the condensed water will be taken out from the condenser. This is an open system. So increase the yield. The system can be integrated with a conventional solar skill where you can get multiple outputs, one from the condenser part of the normal desalination unit and from the solar skill. So the saline water will be charged in the evaporator unit as well as in the solar still, and due to the availability of solar insulation and solar still, this saline water will be partly converted to the desalinated water. The other advantage is that the hot brine will be then circulated through this adsorbent heat exchanger. This will act as a heat source in the thermal compressor. In that aspect, this can be called as a hybrid system. So the desalinated or potable water can be obtained from both the condenser part of the adsorption unit and this solar still. So this is the experiment we have conducted at meteorological conditions of the Kollam here at the Energy Research Lab. And this is another system we have developed. This is the modified form. It is the integration of adsorption unit with the humidifier and the dehumidifier system. This is a sort of combination of desalination and atmospheric water generator system. Again, there we can see an evaporator, adsorbent beds, and the condenser. So the difference is that there will be a blower and the refrigerant, the water vapor coming from the evaporator will be absorbed in the bed matrix, then transfers to this condenser, and this is an air-cooled condenser, and this will be condensed out, and the fresh water will be taken out from here. At the same time, the air blown over the condenser surface will be get heated and then enters the humidifier. At the same time, this hot water leaving from the adsorbent bed will be sprayed over this one. It will be acting as a steam humidifier, and once this air saturated at the point 3, the saturated air will be passed over the dehumidifier. The chilled water leaving from the evaporator will be acting as a cooling medium here. Once it attains the dew point temperature, this atmospheric air or moisture content will be subjected to the condensation, and the fresh water will be available at this dehumidifier output. So that means it is a sort of desalination and atmospheric water generator unit. So this is the modified version of the same system. This dehumidifying unit is integrated with a thermoelectric cooler in order to increase the water yield. Same system, vapor adsorbed here, condensers, desalinated water will be taken here partly, and then the atmospheric air will be humidified, then enters the cold side of the tech unit, and there it will be subjected to the cooling and to the dew point temperature. When it attains the dew point temperature, condensers, this potable water will be taken out here. So this is the photograph of the system that we have developed. You can see this evaporator unit, adsorbent beds, blower, condenser, humidifier, and dehumidifier unit, and this is the heating unit, the heat chamber. So this is the performance of the system. Adsorption alone, you can expect 0.45 liters per hour of water, and if it is combined, you can get the considerable amount of 1.12 liters per hour. So these are the some of the pictures of the buildings or office buildings where these solar cooling systems were integrated, or they convert their conventional cooling systems, VCR, evaporative cooling or absorption cooling systems, into these solar-based adsorption cooling systems. Here we have, this is the Cherry I have mentioned here in New Delhi, and this is Shanghai Research Institute, and this is the most important project. This is the first passive solar building in India. The project started in 2011 and commissioned in 14, but they have used this evaporatory cooling currently to meet all cooling loads. But recently, this MNRE have initiated a project to convert this building into solar absorption based cooling technology in association with dry air industries, and they are actually looking for the composite adsorbent and a suitable mixed refrigerant combination to replace this evaporative cooling technology with adsorption cooling techniques. This is the first passive solar net zero building in India. This is the building. So with this, I would like to conclude my presentation, and thank you very much. Thank you all organizers for this opportunity. Thank you very much.
Sir, there is
There
a
is a hello.
sir, there is a question in the chat box. Please explain
Okay,
about
yeah, yeah. Yes,
current
yes, yes.
research in passive clay-based.
Evaporative cooling, actually, evaporative cooling, there is a lot of evaporative cooling works are being going on. I didn't explore much about evaporative cooling systems because that is not our area of research, in fact. But there are a lot of problems with evaporative cooling or even absorption based coolings or tech based coolings. That is why, being it was, there are a lot of advantages with this absorption cooling systems or a wide variety of choice of refrigerants or adsorbents or even its scalability things. People are mainly focused on this. Evaporative coolings are there for small scale buildings, applications, and all. That's what I mentioned. That buildings actually they have employed evaporative type coolings in India, even in Kerry buildings also. They have employed evaporative cooling systems earlier. Okay, Kiran, hello. Am I audible? Yeah.
Yes, sir, you are audible.
Okay, okay.
Thank you, sir. I think no more questions are there. Thank you, sir, for accepting our invitation and sharing your experience on solar energy.
Thank you, Kiran. Thank you very much.
So, as we reach our end of the 5-day online FDP, we would like to thank all the participants on behalf of Carmel College of Engineering and Technology, Alapi. I would like to thank all the participants for their active participation. Uh, we will update the certificates of all participants according to the uh, percentage attendance. We will share the details within tomorrow or Monday. We will share the details of participation certificates through mails. Thank you. Be on the WhatsApp group for some more days so that we can update regarding the certificate distribution. Thank you all. Hoping your support on all future programs also. Thank you.
Thank you, sir. Thank you, sir.